Okay, so hi everyone. I'm Mara, and I will give you hopefully some insights in how to do data extraction with large language models. Yeah, and we published a paper which was also mentioned in some presentation before, which is about from text to insight large language models for scientific data extraction, and that's what this whole presentation is based on. So what will we do in the next 2.5, 3 hours? I will give you a short intro into data extraction and large language models. Then we will start with the more details and also the hands-on part. And then in the end, I would like to give you some examples on how we actually use data extraction in our group for some real research examples. I put on some schedule here. Let's see how we can stick to this, but it's mainly, so the hands-on parts are, I know that there are different levels of coding skills in this room probably, so we will just do it for like 20 minutes, and if you have some issues doing it, just raise your hand. We try to help you, but if we cannot do it in 20 minutes, I will also give you the solution in the end, so just that maybe other people are not bored, we will just stick to the 20 minutes and then see how it goes. So yeah, you have seen this before, and I guess also in the last 2 days you heard a lot of stuff about why we actually need to have some structured data. And yeah, we made this this figure for the review I talked about in the beginning, and you can see here that there's a lot of potential in scientific publications, and if you compare it to the data sets that we actually have, they are really small. So maybe you cannot see it, but this is like the small gray box, which is represented here. So the scale is, they're on completely different scales. So that's why extracting data is, yeah, one thing you can do to actually get a larger structured data set to maybe do then some machine learning with it. And the question is how we can extract the data efficiently. So we have on the one side those papers that are kind of unstructured in some kind of text. And then on the other side, we would like to have something like this, which actually we can do something with our computer. But how do we get there? So what we could do, and what also a lot of people did, is we could use some domain expert, as I guess all of you are, and then they could extract the data manually, but it takes a lot of time. It's also really annoying. And then on the other hand, some years back, large language models came into place. Yeah, now we try to use those for actually extracting the data automatically, because it's super scalable, and it also doesn't need to, we don't need a lot of human experts to support this process. So I want to give you just a really short overview on how large language models work. Maybe some of you know, but what we have in the beginning is the user query. That's basically could be a question or whatever you have. So that's what you like prompt the model with in like a natural language. And then what happens first is that the language will get tokenized. So this means that basically your question or your query will be like divided, in the simplest case, split it into words, as you can see here. And then also an important topic a lot of people talked about, we will convert those tokens into embeddings. And an embedding is basically just a vector representing the words. So that's a really crucial step. After this, the actual magic happens, but I will not explain this in detail now. So maybe some of you are familiar with the attention mechanism, so that's what's happening here. And then the model actually predicts the next word. This can be seen here. So what you see here is the different words that the model came up with. And then you also have a probability of for all of those words. And then some parameter, which is called temperature, comes into place. And if the temperature is 0, the model would always choose the word with the highest probability. And if it's higher, then it can also be can also select some other word which has a lower probability. And then we get actually a word which then gets added onto the query, and we go on with this process until we reach some kind of end, and then you get a response. So that's just a super quick overview. And there are a lot of resources out there if you are interested in learning more about how these models work. And now we want to use those models for data extraction. And in the data extraction process, it's a little more complicated than just interacting with the model. So we start with the pre-processing, where we actually need to get our papers, and then maybe also need to convert it to text or need to clean it. Then those models can also have a context window, which means that you can have just a specific number of tokens in there, and if you have too many, then the model cannot process it. So we maybe need to split the text into pieces. Then we interact with the model, and there are a lot of different ways on how you can do this. I will comment on all of those things in detail later. And after we interacted with the model, that's a super, super important part, is we actually want to know how good our extraction was. So if you want to extract data and just use some kind of model and then use the data in some kind, you would never know if maybe the model made some mistakes and how many mistakes it actually makes. So this is super important to actually evaluate your extraction, and then you would go over this loop again until you kind of reached, until you are satisfied with the evaluation you get in the end, and hopefully can then extract your data. So yeah, let's go into the details a bit more. So as I said, the first step is you actually need to find your relevant papers. Maybe you have a data set already, then that's a nice thing, but maybe you don't. So maybe you start in a complete new field and you want to get the most relevant papers. So what you could do is you could use some of those tools, Crossref or Elsevier Scopus, that are just two examples. And what you could do here is you can define some keywords that are relevant to your topic, and then retrieve a list of relevant articles. So for example, in Crossref, you have all the articles that have a DOI number, you have all the articles in there. So you'll definitely find some interesting ones. And also before we talked a lot about this, but if you actually want to download the articles, you also have to consider copyright. That's an important thing. But luckily, I guess most of us work in academia, and there are some copyright exceptions for academia in Europe and Germany, which is really nice. So what does this mean? Please inform yourself before you download anything or mine some data. And maybe also ask someone who is someone who is more familiar with some legal restrictions. But what you can do is if your data mining falls under such an copyright exception. So for example, if you work in academia and you want to download the papers and then do something else, for example, you want to extract the data with it and not just upload the papers again, because that would be also not covered with this exception, then you can use some of those tools which basically collect you the full articles from different publishers. So that's super cool, super helpful, but you cannot do this in all different settings. So if you have no copyright exception for the case you're actually doing, it gets a little more complicated. So there are different things you could still do. There are some open source databases. You can try to get some papers. Or the second one is possible, but I think no one really tried to do it before. You could also try to get the permission for each publisher, but that's super annoying. You will never know if they even answer you. So maybe try the other things first, and if nothing works, and maybe you are a super big group and want to extract a lot of data, then you can maybe also try to get permissions from publishers. So yeah, hopefully now we have some papers downloaded. And now I just want to mention this step, which actually comes later, but it's super, super important. So as I said, you want to have some kind of score in the end. So you have your extracted data, you have your ground truth, and you want to know how well do these actually match? How well did the model extracted the data? So normally after you downloaded all your papers, you need to actually manually extract some papers and construct a test and validation set. So that's a step that is annoying and time consuming, but it needs to be done, and it's super, super crucial. So now we have the data. We hopefully made some test and validation set. And now the next question is, what did we actually got? Maybe you only got PDFs. And maybe you want to use a large language model, which means you need some text. So the question is the article machine readable? And if it's a PDF, the answer would normally be no. So what you then need to do is you need to convert your PDF document into text. And there are various tools you can use. We will use in this tutorial PyMu PDF because it works quite solidly and quick. But there are others like Marker and Nougat, which are specifically made for converting scientific publications. So they work probably better for this specific purpose, but they also need more compute. So for example, for those two, you at least need one GPU to run them efficiently. And if you don't have this, I would always recommend you start with the simplest and then see how it goes. And maybe this is even enough. And then, again, you need to check if this conversion is correct. Because for some things like tables or figures, those things struggle. And you will get some mistakes. So you always need to check if there are maybe some mistakes. Because if the article is missing the important information because maybe the table was not converted, then the extraction in the end can never work. So you need to check this. And if maybe all of those fail, then you can maybe try to use a vision language model instead of a language model. But we will come to this later. And then you have an additional step. So if you have some text now, you can also clean the article. And by cleaning, I mean a scientific article normally has a lot of stuff that we are not interested in for the data extraction. So for example, we have all the references we don't care about. We have all the acknowledgements we don't care about. So such things you can basically clean and therefore reduce the amount of tokens you send to your model. Because if you use some conventional model, you need to pay for each token you pass to it or you get back. So you want to minimize the number of tokens you actually send to the model. And now we could actually send some stuff to a large language model. But to just quickly come back, I told you we tokenize our text and then we send it to the model. But all of those models have also, as I said, a context window, which means they have a specific number of tokens you can pass to them. And if it's higher, the number is higher, they will not accept your query. And you will get some error. And that's why we, in some cases, need chunking techniques. Which basically means you would cut your text into smaller parts. So there are different techniques and approaches how you can actually do this. The easiest way would be you would cut your text apart after a specific sequence. So let's say after 1,000 tokens, I would just cut the text in half. This comes with some limitations because maybe you cut a sentence in the middle apart and then it doesn't make any sense anymore. That's why you could also use semantic chunking, which then would cut the text, for example, after each sentence or after specific sections. So this kind of improves those limitations a little bit more. But also, the more modern models have a larger context window and it gets just larger over time. So this problem you maybe will find if you work with some local model or if you want to extract text from a whole book. But if you have some research papers that are maybe like 10 pages long, you would not find this problem. But still, it's important, and sometimes you need to do it. So this leads us to the first hands-on session. So basically, what we now want to do is the 3 parts that I presented to you. You can now do yourself. We try to stick to 20 minutes. Let's see how it goes. And how we do this is you can scan either the QR code or you can go to this link. And there you need to log in with some university account. I hope this works for everyone. Yeah. And then hopefully this tutorial will open and you can start the tutorial. And now we would actually come to the model interaction. And there you have different things you can do. You can do large language models. I told you before, maybe you have some struggles with converting your PDF into text. So maybe it's easier for you to use directly a vision language model. And maybe you heard in the last days also the term agents. So that's also something that you could do for data extraction. So let's go through them one by one. So what you do if you use a large language model is basically what you can do there is basically changing the prompts. So there are two types of prompts if you interact with a model. One is called system prompt. That is basically a higher ranking prompt that will be prominent throughout the whole interaction. And if you work with like ChatGPT in like the website, normally you cannot change the system prompt. So they predefine something in there. But if we use an API, we can define this one. And here you would put something like I said here, you are a chemistry expert extracting data from publications. So you kind of try to give the model some personality. And there are some, I would even say, funny studies that, for example, also prove if you put in here, you have an IQ of 120, the performance can also increase. So there's a lot of stuff going on in the system prompt. I would just try out different things here. And the only thing is you shouldn't make this super long. So the main thing you actually put is in the user prompt. And that's where you would put whatever you want to do. So in our case, we want to extract, for example, all chemicals from the publication, and then you would input the text that we obtained before. So that's the simplest thing you can do. Then there are some more advanced prompting techniques that I just want to cover super quick. So something you can do is called one-shot or few-shot prompting. What you do here, system prompt stays the same. The user prompt is a little different. So what you put here is an example. So you would basically provide an example publication. I kept it super short here. So the product was solved in benzene. And then you would put the answer you actually want to have in the end, so benzene. This can help in like other applications. It was shown that this could definitely help for data extraction. I think no one has yet proven it. And from our experience, it didn't increase the performance, but I just want to mention this quickly here. You can try it out because it's super easy to implement and maybe it improves your performance. So that's what you can do. And what you normally do is just trying out the different models because we have some models from OpenAI, from Anthropic, but also some open source models you can run locally, for example, the Llama models. So what you would normally do, what is basically the main impact of your performance is the model. So you would try out different models and then see whatever model gets the highest performance. And try these out. What we are using are mostly some leading models from Anthropic or OpenAI because they work the best for us. What do you do if nothing works? I just want to mention this shortly. I think no one has really done this, or it's not super easy to do. Is something called fine-tuning. So basically, if none of the models work, you could also try to get a lot of data to use some open source model like a Llama model to fine-tune it. So what you would do here is you would need to have your input, which is the paper and your prompt, and then the desired output. And with this, you can then fine-tune a model, but normally you don't have thousands of data points to do this, and it's also, for a non-expert, not super trivial, so I would not recommend you this. Just try out the models, they probably will work, and but it's something I have to bring up,
Is it possible to ruin the performance of an LLM?
Oh, for sure, for sure.
Okay. So it's quite risky.
It's not super easy, I think. I think for some hackathon, we tried to fine-tune, not for this, we tried to fine-tune some model and completely ruined it. So it was just giving us nonsense after that. So for sure, it's, a lot of knowledge is needed to do this actually properly. So that's why I just bring this up here, but would not recommend you doing this. And you also anyhow not have the data. If you are at this place where you annotated 1,000 of papers, I guess you not even need to fine-tune the model because you already have your extracted data. Or that's, but to bring it up, that's a possibility. Okay, so before I said maybe your tool to convert the PDF to text or whatever to text is not working. Or maybe you also have figures in your publication. I think in a lot of scientific domains, we have a lot of plots, images, or whatever. And maybe your information that you're interested in is in those figures. So what you could do is using vision language models. So what they are doing, they are basically would convert your PDF into image. That's super easy. And then you would parse the image with the text prompt together to the vision language model. It would process it together and then come up with your structured data. So that's a really nice thing to try out if nothing is working. One of the limitations would be that sending an image to a model is a little more resource intensive. So it would probably cost more because the image will consume more tokens. So you need to consider this. And also, Nawaf introduced one of our benchmarks. We tried there also some kind of data extraction tasks and try to see how good models understand plots. And they are actually not as good in understanding plots, so try it out. I would not be surprised if it doesn't work great, but for extracting text, for example, it could work. And then as I said, one thing you could also do, and that's maybe more something people would do in the future, is using an LLM and also equipping it with some tools. So as I said, you could have plots in your paper, and right now those models cannot extract the plots perfectly. So you maybe have a tool that extracts actually the plots. You maybe have a tool that extracts tables. In chemistry, we have a lot of those reaction schemas. Models also struggle to extract those. We maybe even have a tool that validates our extraction directly, or something that ensures that our schema is updated. So this model could then interact with all of those tools, and then probably the performance would be higher. But that's just some concept. I think it's not yet perfectly implemented, and this would also require a lot of more work than just using some ready model. But if you, I don't know, want to extract 100,000 of papers, maybe this would be an option for you to build a more complex setup. And this leads us to the second hands-on session. So this is basically, you can interact with some models and try out different prompts and see what changes here. To do this, we need to get some API key. As I said, normally you pay for this. This is a free key you can get. So please scan the QR code, or you can also just search for Grok. So you need to sign in there with, for example, a Google account, and then click on creating API key. And then you copy it and insert it into the notebook. This comes with some rate limits, so if you actually want to use it for maybe some data extraction, this might crash the limits, but for this tutorial it works. And then you can also just get some API key for example, from OpenAI, but then you actually need to pay for this. So we are using this now, and this is also not the leading model, so I would expect better performance if you use some other models, but we will use this for the tutorial. So now we are actually in the last part, which I said in the beginning is super important, and we will go through this now. Okay, so what you can do to increase your performance after you actually called the model is using something called constraint decoding. What does this do? So for example, if I want to have a temperature, I know that the temperature is some kind of number. So if the model gives me this as an output, 1 at, I know that's not a valid temperature. So what you can use is something called constraint decoding, where you define a schema beforehand, and then define that, for example, this value temperature that I'm extracting should be some valid number. So it knows these ones are the only valid outputs for the extraction. And how you do this in practice is using something called Pydantic. There you define such kind of structures. So you define some classes, and in those classes you can have different things. So this is an example for some polymer data extraction. So what I have here is some name. I want to know the name of the polymer. And in any case, I want to have this name, because what you can also do is putting some keys to optional. So if this entry is not extracted, the model doesn't care. But if the name is empty, then the model cares and actually says that this is not a valid output. And what I can also define here is the type of output I want to get. So for the name, it should be a string. And then I provide some description of what this actually is. So here we have some short name, which is optional. We have the amount. Here I defined another class for any kind of unit, because for a unit, I always want to have the value itself, but also the unit with it, and maybe some error bar. Then we have, for example, the purity, and that should be a number. Concentration is, again, some kind of unit value. And then we have the supplier, which is a string. And with these schemas, you can get completely, you can build like really complex schemas, and that helps a lot to ensure that your output is actually the one you want. So this can already improve the performance, which is super cool, and it's not super complex to do, so you should always do this. And then the actual fun starts, because we need to do the evaluation. So here we have some extracted data. Just some examples, we have some molecule with 2 values. And here we have our test and validation data. And now the first question is, how do we actually compare them? Because maybe the model extracted 3 molecules, but in our extracted data, we have just 2. So which of those do we compare? Or maybe the model hallucinated and extracted some stuff that is not in the test and validation data and is actually completely wrong. So the first thing that you are doing is doing matching. So you try to find the extracted entry that is closest to your test and validation data. Because also, I colored things here a little, also the model could do things in different order. So you need to actually match the things here to be able to actually calculate in some score. And how you do this, there are different techniques. We will see this in the hands-on part then. One example for this. What you can, for example, do is taking your most relevant entries. I mean, in this case, we have just 3, so we can just take all of them. And then applying something, if you have a lot of strings, you could apply something called fuzzy matching, which is trying to calculate the closest distance of 2 strings. If you have just 2 numbers, you can use different things. But yeah, that's the first step here, so trying to match the things that are actually close to each other. So if we are done with this, we can do some other things to make the evaluation easier. One thing is normalization. So maybe the model extracted our values with different units. So there are some easy tools to normalize things, to all have it in the same unit, to actually compare the same things. And you could also have some first verifiers in here. Or do other things, like, for example, if you have chemicals, maybe the model also extracted the name slightly different. So if you would just compare the strings, it would not count as a match. But for chemicals, you can, for example, convert the chemical into smiles and then compare the smiles. So there are different things you can do here to make the comparison then easier. And then we are now actually at the step where we want to compute some metrics, some score. 2 super easy metrics that you can always try to get is precision and recall. So what we see here are our extractions, and here we have our ground truths. And you see here some of them are correct, some of them couldn't even be matched because they are completely different. So what we see here, we have 1, 2, 3, 4, 5 correct entries. So we divide with the precision, we divide the correct entries through all of the extracted entries, so for all of these. So in this case, we get 50% precision. For the recall, we divide the correct entries by all the ground truth entries. And then you could actually also calculate some more complex metrics, but these are like the basics you should always have. And if you can automatically score your extraction, then this is super helpful because then you can optimize the whole process and see what, for example, a prompt, if you change the prompt, what kind of impact it has and if the performance goes up or down. And in the end, you also want to know how many because you probably will never go to 100 of one of those. So you would like to also know how many mistakes are actually in my extraction and if I'm maybe fine with this amount of errors. Because even if you would do it by hand, you will probably also have some errors in there. So this is super important. Yeah, and if you do it right, it helps you a lot. Yeah, now we will see how we actually do this. So now you can go to the third notebook. So you will first do this constraint decoding, and then you will do some steps of this matching and score calculating process. And we will do another 20 minutes and see how it goes. So this is how the notebook should look like. And you can again raise your hand if you face any issues. And this time you just need to open the notebook. You again need the API code, but you should still have it. So, as I said in the beginning, this is all covered in some review we wrote a year ago. And then we also have this online notebooks with even more extensive examples, also some like actual application examples. So if you want to know more about this stuff, you can check these. Yeah, and now I want to actually talk a little bit about how we actually use data extraction in our group, about my own work and about what my colleagues do, because there are some little tricks and more complex things that we use to actually make it work. So first, about my colleague Mailing. So she wants to extract some data about micelles, about polymer micelles, and how they distribute in some organs in the body. And what is special about her workflow is that in her data or in her publication she wants to extract, there are a lot of figures. And actually those figures matter to her because that's the important values she wants to extract. So that's why she made a combination of extraction with large language models and vision language models, and then combined it all together. So that's what she does with the figures. She first tries to find the figures with the same module we already used to convert the PDFs into text, PyMu PDF. Then she also tries to get the caption for those figures. And then she passes the figure with the caption to a vision language model and then gets some structured data from those figures and then combines it together with the text and then extracts the rest of it. She just started with this project some months ago, and I must say, and that's also what she said to me, that this part is not working well right now because, as I said, the models are not yet super capable of actually extracting so the idea would be to actually extract the exact value from this figure because there is no raw data with the publications. And this is right now not working great, but that's the first initial attempt, and maybe she will use some specialized tool for this, or maybe the models get better. Yeah, that's just some use case that is not yet perfectly working. Yeah, so that's my own data extraction. So what I try to extract is information about polymers. And as you see, I already extracted all my data. My pipeline got quite complex. What is, I guess, the most interesting part here is this thing, because I have some filters before and after the extraction to actually ensure that the scores are high and I don't extract any false information. So what I did here, I tried to filter out papers that are too bad to extract. And with bad, I don't mean like the scientific quality, I mean the actual visual quality, because I extract a lot of old papers and some of them are just not readable. So what I try to do here, because I cannot like score the papers or filter them out manually, I again used the vision language model and asked it to give me those scores of the papers. So I basically asked it to give me a score for the overall PDF quality, the table quality, and the quality of the numbers. I had some additional features like the reaction numbers, language, and publication date. And with all of those features and like 40 papers, I then trained a super simple random forest classification model to filter out papers that are highly having a high probability of actually being extracted wrong. And this way, I could increase my like precision up to 20% more than it was before, which is super nice. And that's one approach I'm using to actually increase my scores for the prediction, for the extraction. And then shortly to my colleague Martino. He also just started with the data extraction. I think that's like the end goal. And you see that he also wants to do something with agents. But that's not the most interesting or developed part. What he's doing is he's extracting organic reactions and has a super large schema of stuff he wants to extract. And then actually doing those evaluations that you just did is super annoying and maybe not even possible. So what he does, he's using another LLM to judge if the extraction is correct. So what you see here, he again also labeled some data himself, and then he got the extracted data. And then he asked some LLM again to evaluate each step. So in some synthesis reaction, you have multiple steps. So the LLM looks for each step if the extraction matches the ground truth. And then it will calculate or give out some scores. And based on this, he then knows how good his extraction is. He also has a second part to this whole pipeline, which is then actually trying to optimize the prompt. I told you before that optimizing prompts is also not super easy. So that's why some people, not only for data extraction, also in general, try to optimize the prompt in some more systematic way. And one way is you could use an LLM actually optimizing the prompt. That's what he tried here. Problem here is that you need a lot of iteration steps to actually make this work. And so I think he would maybe also not recommend doing this for this specific example. It was more kind of a study of if this can be helpful or not. But I think the really interesting and helpful part is using the LLM to judge your data extraction, because might be a lot easier to do it like this than doing it with some rules you defined before. Yeah, and that's also the end of the presentation. So if you have any questions now, you can ask them now or also reach out to me or my colleagues later. So that's the lab I'm working in. Yeah. Are there any questions?